This question is a probability one, and it's asking us if we have 180 out of 250 people that have been sampled, what is the um, confidence interval to be 95% sure that we've gotten a correct sample? So I'm going to move over to the right here to give myself some more space. And so what's key about this one is that our n is equal to 250, all right? And our confidence interval, and therefore our z-score, is equal to 1.964. Okay, so where did I pull all this maths from? I'll just make it 1.96. That is okay. So what we've done is we've got all the Fremantle residents, and some of them are saying, no, I don't want it. I don't want the vote. I don't want the port expansion, sorry. And some of them are saying yes. Okay, so when I take a sample, right, I want to know how this is reflective in the total population. So I've got my bell curve, and I'm trying to say if I take lots and lots of samples, I'll generate this bell curve. If I take like 100 or 200 different samples of 250 people, I'm going to generate this bell curve. But for now, I've only taken one sample. So in my sample, the probability of success is equal to 180 divided by 250. Now this is a calc-assumed question, so go on, get your calculator, and don't bother simplifying it in your head. There's honestly no point. So get the calculator out, and it's out of 250. We've got 180, 0.72. So that's telling us, hey, for this particular sample, right? We've got 0.72. So we're just going to assume that's our mean because that's from our sample, right? But when we take another sample, it could be anywhere else. Maybe it's down over here. So the question is asking us, what's the bounds, right? What's the bounds from here to here that says this is 95% of the probability and that there's only a little bit of probability either left or right? So we've figured out that, but we need to figure out our, I guess, standard error in a way. And so that is equal to, I guess, this distance, okay, from here to here, okay? And that standard error needs to be multiplied by the z-score, okay? Because the z-score tells us how much of the bounds are there. Do we want 95%? Or maybe, so that's 95%, but maybe we want 99%. So that's why we need to times by a bigger z-score. You should really memorize the following z-scores. I'm going to write them down for you now. If you have a confidence interval of 90%, okay, your z-score, the little hash there, is going to be equal to 1.645. We've already done 95%, but I'll write it down again. So you should memorize these. And then we also have 99%. And that is equal to 2.576. So we are going to use this. Okay? And now we need to go to our formula sheet, right? When we go to our formula sheet, we might see that there's this confidence interval, and it's a really, really long equation. And let me break it down for you. So it says p hat minus z, right? Z, and then it's got this other looking thing over here with p hat 1 minus p hat over n is less than or equal to p. And then on the right hand side, you've also got like another thing that's quite similar, except this time this value there is a plus. Okay, so what does that mean? Well, the p hat here right? That's our sample proportion, or that's like when we took a sample, what did we get? What's the probability of success? And in this case, it's equal to 0.72 for our example here. N is the size of our sample. In this case, it was 250. All right. Z is basically how much you want to be confident about it. Is it 90% or is it 99%? That tells us how big the bounds are here. And then that other crazy thing, the like square root thing, tells us the distance from here to here. Okay, the standard error. Okay, but it would tell us the standard error if we had a bell curve where our mean was equal to 0 and our standard deviation was equal to 1. Okay, so that's why we need to multiply it by our z-score. Okay, so really, this is the big long equation that we need. You can find it in your formula sheet. So let's make life a lot easier and let's just figure out what z p hat p hat and then n is equal to, right? If we figure out that, then we've got the whole equation. So it is 1.96, all right, all divided by here, and then we've got that 0.72 minus 0.72, and then all divided by 250. And then we can say use calc, let the marker know what we're using, and it'll just make their life easier. So let's go across now and grab our calculator. We're going to times 1.96 times by 0.72, 1 minus 0.72, and then all divided by 250. Okay. And that gives us this value here. Oop. And this is our margin of error in a way. Okay, you might have seen that. So again, going back to our bell curve, we've taken our one sample and we guesstimated from our sample that our population is somewhere around here, but we're not sure. The actual population is going to be this pink line. Maybe it's over here, but we don't know. Maybe it's over here. So we're just wanting to be 95% confident, okay? So what we've said is that we're allowed to be this far away from the mean of 0.72. So we're allowed to be 0.0556, okay, away. So this here is our margin of error. And now all we need to do is figure out the lower bound and the upper bound and give it to the marker as like a point. And then we're like write a sentence and we're good. So what is the lower bound? Well, it's 0.72 minus this number here. So that's why you get this like crazy p hat minus, and then that z with the square root and everything is just your margin of error. Okay, so that's okay. Let us figure out that, and we can say that the lower bound is equal to 0.72 minus by what we figured out, 0.0556. And our upper bound, okay, our upper bound is equal to 0.72 plus 0.0556. And if we use the calc, we can quickly figure that out without having too much effort there. So we can go 0.72 minus, that gives us that lower bound. Okay, and then we can give it a plus. Okay, so let's just round to a couple of significant figures and convert it to percentages. So we can say that 66, we can say to be 95% confident. Okay, to be 95% confident, um, the um, yeah, so we can say that we can be 95% confident that between 66.4 and 77.5 of Fremantle residents do not want the new port expansion project. So the bounds are 66.4% and 77.6%. Okay. Otherwise, you can say CI with 95% is equal to, and then just write it out as and this guy here. Okay, there we go. Okay, so now let's go back across to part B here. Okay, part B is saying what is the error margin of 8%, and we have a z-score, or we have another 95% confidence interval. Okay, so this one is our z-score goes back to being 1.96. Oh, let me write that out correctly. 1.96, and we have our error, which is equal to 0.08. Okay, so we're 95%. Okay, so we don't know the probability of those in favor, and so like we don't know our sample proportion. So in this, we're going to use an estimate. Okay, when we don't know, we're just going to say that it's equal to 0.5. Okay, so at 0.5, we've got, like, we haven't done a sample, it's just working the maths here. Okay, so what we're trying to figure out in this question is what sample size should be used. Okay, so what's the sample size that should be used? So that is what we are trying to find. It's a little abstract because you don't know the sample proportion, so we're going to assume that 50% are in favor and 50% are not in favor. Okay, and again, we've got a bell curve and it's around here. And what we're trying to say is that our error, right, our error is allowed to be from here to here, and that is 0.08. Okay, just that distance there. But we want to be 95% sure that everything's in there, so we've got that z-score of 1.96. Okay, so what we're going to do is rearrange our margin of error equation. So that equation is on your formula sheet, and it says that E is equal to Z with the square root p hat 1 minus p hat all over n. So let's substitute everything in and solve with the calculator because we've got the calculator. Okay, so we say that E is equal to 0.08. Our z-score is equal to 1.96. And square root here. All divided by n. So use calc, solve for n. N is equal to, and let's grab our calculator. So 0.08 is equal to 1.96. 0.7, I actually used 0.72, didn't I? That's meant to be 0.5 because we've changed question. I've gotten into the zone of using the old one. So these ones here are just meant to be, that 0.5. 0.5. Okay, so a little messy, but bear with me. And all divided by, I'm just going to put x here because it makes it easier to solve. Uh, Advanced solve for x. And we say that x is equal to 150.0625. Okay, but we can't have decimals there, right? So we round up. So we say the sample size should be 151. And there we go. That is that there. So, okay, this next part C is asking, what happens? Uh, what is the sample size? Or what happens to the sample size? Or what is the sample size if there is a 90% confidence level instead of our 95%? Okay, so what that means is that our z-score drops, right? So a margin of error is, if we go back to the equation, the margin of error here is our z-score multiplied by our p-hat, all divided by n. So if we keep this number the same, right, but now our z-score is dropped, then what we're going to find is that it will result in a um, smaller sample size. But what we need to do here is rearrange, first of all. So rearrange for n. Okay, and you can either rearrange for n using a calc, which is what I'm going to do. So we've got E is equal to Z P. Now, sometimes it's a bit hard to find all of that, so you can go to ABC and then use these values here. It does take a little while, but there we go. We get given this. So you can go back to the ABC and then put in all your values. So we can use calc and we can say that n is equal to the z-score squared. Okay. and then P all divided by E squared. Okay. Now, the key thing is that our confidence interval, that z-score, has changed. All right, so z of 95 is equal to 1.96. But the z of 90 is equal to, right? Um, that is equal to 1.64. And finally, you can therefore say that as n, or as z decreases, so does n. Okay, this will require a smaller sample size. And there we go.